So next up, we got Run here with another port for this time RISC-V, a non-traditional one. There you go.
Okay. So I thought I'd quick mention my background in RISC-V. I've been working in it for 13 years now. I wrote the first real non-Berkeley firmware package core boot for RISC-V, and funny story, HP got so upset about it. I was presenting it in 2015 that they presented a paper on UEFI for the RISC-V, and it turned out that didn't actually exist. But they didn't want to just see an open source firmware thing up there, so they put it in. I was on the board of lowrisk.org for 5 years. We did the Open Titan work at Google, and LowRisk was the provider for that. I did my first Plan 9 port to RISC-V in 2016 with Harvey, and then I also did the Orvoot initial port for RISC-V. So a lot of this processor is familiar to me, but I learned this time around that things had changed in ways that I didn't expect. So this is the non-traditional aspect of this. And so the decision I'm going to describe is proving to be a little controversial, kind of inside game controversial. Most people wouldn't care, but I thought I'd talk about it. And then I realized it was interesting to step back and see where it all began. So let's see if I can. So I'm going to do this really simplified overview of 55 years of what we've been doing in Unix and its descendants, and then how RISC-V and security have turned that on its side, and then talk about the port I'm doing and how it breaks with Plan 9 practice. So in the 70s, you had a PDP-11 and it didn't have virtual memory, and DEC said, don't worry, we're going to help you out. And they would sell you that card up there, and they would sell you a set of instructions how to rewire your processor. That's a 5-step process there so that the card would work because it interposed in the backplane. And when you were done, you had 8K pages in your 64K address space, and it was the same address space for user and kernel. And how did then kernel get data out of the user address space if it was the same address range? They gave you also an instruction which came with that wiring, move from previous user and move to previous user. And what it meant is put an address in a register and do this instruction, and you get back what was in the user memory at that place. So those two page tables were active. And if you're used to x86 and RISC-V, that's not really how it works on those. You only have one page table active at any time. So there's kind of the first difference from sort of common expectations. Anybody who reads the Unix v6 source has seen the term segment and might wonder why the term is segment. It's because this defined a 256-byte aligned address in the page, and that kind of was the length of it, so you could have sub-pages. And on top of that, user programs could modify their own PTEs. We were still learning. Okay. So the VAX11 cleaned all this mess up. It came with a full 32-bit address, and for reference, the first machine I know of that gave you 4 gigabytes of memory was 1986 with the Cray 2. So this is like long before that. And so they said, gosh, you know, we're going to deliver this with 128 kilobytes of memory, and we've got a 32-bit address space. Let's do some clever things. And so they took these top 2 bits, and that's your processor privilege level. And the higher order bit set was kind of what Unix used, and was the highest order privilege. And then both bits being 0 was user mode. And user mode got this impossibly large gigabyte of potential virtual address space. Data General Eclipse flipped it, which caused no end of problems because it turns out a lot of Unix programs, including the Bourne shell, use null pointers like crazy. So you hear nowadays, oh, null pointers, nobody uses that. Well, back in the day, null pointers were very commonly used because the address space was so small. So that's kind of where that's a fun read, by the way, if you get a chance. But and then they grabbed random bits in the PTEs to mean things. But the big thing here is higher bit set means you're highly privileged. The 8386 cleaned this up a lot. This is like 10 years again after the VAX. And everybody is so used to this that we don't even think about it anymore. But basically they defined a 12-bit page, 4K byte page, right? And that's your offset in a page. And then 2 levels of directory. And what's kind of slick about this and why people like it a lot, a 12-byte page is 1,032-bit words, 1,000 32-bit words is those page table entries that defines every entry in that directory, and that's 10 bits worth of addressing of the directory. So that's why you get 12 bits, 10 bits, 10 bits. Each of those directories is 1,000 elements, and it just all nicely fits together. It's really great, right? It's very, very clean. And you know, there's no hardware convention here, or architectural convention, but everybody said, let's keep going with that high order bit because it really works really well. So, you know, C and 7 zeros is the top gigabyte reserved for kernel. Notice user space got a little more room. And then we got the AMD 64. Everybody wanted to preserve the 4K page, but PTEs are now 64 bits, which means 512 entries, which means you need 9 bits. And so we go 9 bits. This is a big range, 63 bits. All right, we'll take 4 9-bit fields, okay? And we'll ignore the top 16 bits of the virtual address, and that'll be great forever, right? And it's not that great forever, and so what they've done recently, there's another 9 bits here, and you've probably heard of 5-level page table addressing. And notice if I add another 9 bits, I still can't use all 64 bits of the address, right? And if I add another 9 bits, I go beyond. So I think we're going to be with not quite using all 64 bits until the 128-bit RISC-V standard gets baked, and then we'll start to figure out what to do. But I can't imagine that we're going to keep doing 9-bit stuff like this, right? Now, if you ever wondered, you know, you saw the Nix talk maybe last year, why did we go with 2 meg pages? Because it allows us to slice off that bottom level. That meant shorter page table walks. But another thing to keep in mind, if you build your system around this many page tables and you have like 2 gigabytes of memory, you're going to be doing page table walks you don't need to do. So you compile the current RISC-V 9K kernel, you compile in the number of page table walks you do, you know, when you build it, and you're either going to end up building it, doing page table walks you don't need to do, or not being able to address physical memory because you didn't build it with enough page table walks inside. This is one of the things that's been bothering me about our current port to the RISC-V. The other thing is, you know, when AMD actually came up to us at Los Alamos in '03 to give a talk, and this is one of the things they talked about. There's a big hole in the address space, right? Why would you leave a giant hole like this in the address space, right? Physical address space. Well, think about it. You said the higher half is this higher order bit set, and the lower half is the higher order bit clear. And if you follow that logic through, you're either going to have all the bits represented, all your data path on your processor, all your adders, all your muxes, everything will be there with all 64 bits running power hungry and hot. Or you'll say, nope, we'll let you rip the physical address, virtual address space in half, and we'll give you the higher order and the lower order part. We'll leave a big hole in the middle, and then you won't need as much power and you won't have as much thermal load, and you don't have that much memory anyway. This is a great idea. We'll leave a hole in the middle. And after a while, well, people had a little more memory than this, so now the hole got smaller, right? It will never be the thing on the right because the top 7 bits are kind of unusable. So I don't think that happens until we get 128-bit CPUs, and I hope I won't be alive for the next 256 CPU, or, you know. So I'm not expecting that to happen. Now, the other thing, little history. We started the 9K effort in 2005. That was a DOE, Department of Energy funded effort that I ran out of Los Alamos. We paid Charles Forsyth to do the compiler that year, and Charles did a really great thing. He looked at the AMD 64 and said, this is kind of not really a 64-bit CPU, right? There are instructions that are kind of 64 bits. There are a lot of instructions that are like load it into racks and then move it to another register. You know, it's a funky CPU. Why is that? They added an 8-bit prefix to the instructions of the 32-bit machine, and it has subfields, and the subfields say, oh, if this bit is set, that means the high half of the 16 registers. If it's clear, it's the old registers. So it is an incredible balancing act they did, but it's a total hack. So what GCC said is, oh, well, it could be a 32-bit machine, or it could have different data size or whatever. GCC, you have 4 compilation modes for the compiler. What Charles did is he said, you know what? you'll get 2 GB of code, 2 GB of data. You know, when you build it, you'll have arbitrary pointers for the heap. And what he ended up doing was giving us one compiler mode, right? You compile it and it works. And that actually, I think, followed through into the ARM. But I also know it followed into in Go, because what happened a few years later is the Go guys went to Bell Labs and said, hey, you've got a compiler for the AMD 64, can you send it our way? And we did. So we actually modified the Go linker at Google, which followed this model, so that we were still limited to 2 GB, but we could put it anywhere in the address space. That was for the gvisor project. But anyway, there's your high order bit again. Lots of S and then the C. Notice that C is in the top few bits of the lower 32 bits. That's kind of where that comes from. But notice that only represents a gigabyte. What if I have 32 gigabytes of memory? Oh, I'll put the gigabyte, the first gigabyte of memory at the very highest part, and I'll take the rest and I'll put it at a lower part. And in fact, what I'll actually do, I'll put the very first gigabyte of physical memory here, and then somewhere in here, I'll put the next XY gigabytes. So it's like there's a wrinkle, right? We've got like this weird folded address space. It always drove me a little crazy. And you know, so you see everywhere in the code stuff like this. What's the physical address for this thing? Well, am I greater than or equal to K0? K0 is that virtual address for the very top gigabyte. Otherwise, I go down a little bit and I do this other thing. K limit is the bottom of the canonical address space, and what K limit is depends on compile time decisions.
And this is all really clearly documented in the kernel.
You know, it is if you wrote it. Okay, then came meltdown and all this other stuff, right? So remember, a process in Unix got this page table. And the page table has all the user addresses and all the kernel addresses, right? So if a user does something nasty, like do stuff that sort of drives speculative execution about kernel addresses, they can learn things, which they did. And so this is where you see kernel page table isolation come along. You basically flip to a different page table route when you enter the kernel. And you take the 10% hit in performance to do that. And a company like Google, think about Google, let's just say 5 to 10 million machines, you now multiply their throughput by 0.9 to make that decision. It was expensive, but you had to do it. And that was just the beginning. You know, the next thing that comes in is a thing called supervisor mode access protection. Remember how I mentioned on the VAX, the kernel could say, here's a pointer to user mode. I'll just use it, okay? That's going to go away. And the default mode on the RISC-V is for that not to work. And you can ask me how I found out, right? So, you know, I started this port again, and suddenly I can't reference user mode from kernel mode the way I did 10 years ago. And, you know, ChatGPT explained the situation to me. So I did find a use for that stuff. And, you know, my eyes about fell out of my head when I realized what had happened. So if you turn a RISC-V on and you load a kernel and you don't set the proper bit in the supervisor status register, you can't touch user mode from kernel mode. And then again, as I mentioned, you can't have it all, right? Notice, you know, 56 or 57 or none of those things are 64-bit addressing. You're not going to be able to use the full virtual address. So, little digression here. I had an argument with the RISC-V guys about 11 years ago, and I said, look, I know from my HPC background we've determined that 64K pages are actually a really better sweet spot than 4K pages. And one of the people I was arguing with was Patterson. But so I said, can't we do this, right? Now we've got the full virtual address. We've got a page size that actually is reasonable compared to 4K. We're building like 8 terabyte machines, and we have 4K pages. This just doesn't make a damn bit of sense. And the quote that I got back was from this kernel guy you may have heard of, who said, oh, I think 64K pages are insane. Now, what's actually happened since then, they've had to go through a lot of machinations with the RISC-V in order to enable 64K pages, and it's pretty nasty. And if we'd been able to do this, it's kind of a might have been, we might have had a nicer situation with the RISC-V. So we didn't have to do what we did, but we did what we did to be compatible with the x86 short form.
So who would these kernel person?
Huh? Who said that? Well, you can Google. It's Linus. So yeah, and I thought at the time he was wrong, and he probably still thinks he's right. I still think he's wrong. I know though, in the HPC community and high performance community, 4K pages are just a headache. And again, 8 terabyte machine, it's nuts to have 4K pages. Huh?
Fill 4K with a bunch of doubles.
Yeah, it's nuts.
It's no numbers at all.
Now, there's a really, really nice aspect of RISC-V that gives us a lot of really neat options. There's a higher privilege level mode than kernel mode called machine mode. In machine mode, there is no virtual addressing. So it's kind of, if you think about what would an 8008 look like if it's 64 bits, that's machine mode. And you can do things in machine mode and put privileges in machine mode that sort of allow you to avoid having the kernel do too many bad things, right? If we were to start kernel addressing at 0, then the pointers are interchangeable between those two modes. Now, I have a server part at home from a company that I'm hoping will be announced next year. The trap time from kernel mode to machine mode, if you don't do a lot of context saving, is about 5 nanoseconds. So you can take a trap from supervisor mode to machine mode and make a decision to do something and get back, and I've done this for some stuff, in less than 10 nanoseconds. So if you manage your machine mode trap carefully, it can be very, very cheap. Unfortunately, what they have been doing on RISC-V is re-implementing all of UEFI and ACPI and all this other stuff. And the first thing they do in this standard firmware in RISC-V is save a whole lot of state to stack. So they actually can't get a round trip down to their machine mode handler and get back in less than about 200 to 300 nanoseconds. So, part of this effort, and I'm not going into this because I didn't have time to write the paper, and a lot of people had questions about what I'm doing with the address space, is I'm going to pretty much ditch every bit of firmware on RISC-V and replace it with something that's far simpler, because it can be very fast, and you have a lot of capability in this. And by the way, the 9K folks have shown that they can run a Plan 9 kernel in machine mode, so in that mode where there's no virtual memory. Now, the cool thing about that is if your kernel is not using virtual memory hardware, it can't pollute the TLB. So the pressure from the kernel and the TLB vanishes because it's not using it. I think this is Jeff Collier. He does a really slick thing where we're enabling the Plan 9 kernel to run in machine mode, and that's a research area we really want to be looking at. I've talked to people in the Linux community, and they've just said flat out, Linux will never do this, period. It is simply not possible for Linux to do this. So, adding on to that, there's a thing we learned at Sandia when we were working on the Blue Gene machine. This is 08 or so. John Florina and I spent a couple of days just watching all the system calls from typical Plan 9 usage. And remember, Plan 9, thank goodness, doesn't use swap anymore. So once you get a page allocated, it really shouldn't be moving around. We saw a very, very, very small number of unique addresses used in system calls. In fact, it was like 8, And generally, a system call, the I/O sizes were also very small. What that means is you can actually cache virtual to physical mappings, right, in the proc struct for a process, such that if you had a system call, you could look at that virtual address and say, if I cache this one, I know what it is, this physical address. I can skip worrying about accessing user mode. System mode access protection can be enabled, but I don't have to do a software walk of the page table. So, and it gets back to Plan 9's kind of light use of the way it uses data. So this result kind of implies the Plan 9 kernel could get away without really mapping user virtual anyway. So the kind of summary, kernel page table isolation is a thing. You really should do it. RISC-V does require that you have this trampoline because there are not 2 page tables active as there were in the 1970s era PDP-11. Okay, it's pointed out to me the ARM64 does have that, but RISC-V does not. There will always be this kind of common area you have to have when a user process traps. It's got to trap somewhere, and that has to be addressable from user mode, right? Direct kernel use of user addresses is discouraged with SMAP. The RISC-V machine mode and supervisor mode share pointers, so it'd be kind of nice if you didn't have the wrinkle in the virtual address space and all this other stuff, because you might want to give a pointer and have it be persistent to machine mode. I'm not sure about that, I don't know, but there's a lot of questions here. Plan 9 user pages, once you allocate them, tend to not move around. Plan 9 programs use a limited number of addresses for system calls, so caching should be actually fairly easy of the virtual to physical mappings. And this is another neat thing about Plan 9. Even the most limited RISC-V canonical address space looks like infinity memory to Plan 9, right? I mean, when there was an OLPC in that museum yesterday, right? And I tried like hell to get OLPC to use Inferno because that thing had 32 meg of memory and 32 meg looked like infinity to Inferno. Whereas the Python, it looked like about 100th of what it wanted. So, you know, and the OLPC died because of that Python environment, the sugar environment. But we ran Inferno on OLPC, and my God, it was great. You know, so Plan 9 is very economical in memory, always has been. So here's what I did, and this is the controversial part. I start my kernel virtual addresses at 0, and I go up to 36 bits worth. And then user processes run at 36 to 37. I think that's enough for a while until we try to run Chrome. And we don't ever want to do that. And then everything gets easier. Here's an example. Is this a kernel address? Is it less than k limit? Done, right? And that can be a macro, that can be a inline, whatever. It doesn't matter. It's a piece of cake. Here's what address spaces start to look like. This is when we run out of 37 bits, right? So right now, it looks like kernel here, user here. Over time, it might come to look like kernel here, user here. So these guys have the same virtual addresses to different memory, okay? This is just like Unix in 1970s. So we've actually been here before. And not only that, though, the funny part is this is more restricted than Unix in the 70s. We're never going to get to use a user pointer anyway. Let's see, where am I on time?
Good.
Okay. Another few details. And I just put my kernel base address at 4 gig, right? The memory I actually use is at 4 gig. This is the easiest way to find mistakes you've made with 32 bits, right? I actually wire off the 2 gig to 4 gig region. It's not accessible. You have to leave the 0 to 2 gig region, that's I/O. But I just cut it off, and the two things you avoid, same way as x86, nobody uses the below 1 meg because all the bugs in the BIOSes, right? I don't trust OpenSPI as far as I can throw it, so I just say OpenSPI, you on the low 4 gig, I'm not going to go there. I had an issue with QEMU wanting to load the kernel at 2 gig, so I'll show you the code in a second. My kernel now relocates itself to 4 gig first thing. And I link programs at that. I made the change to JL. That change to JL is not really needed. It can be done with the /RISC-V makefile. So here's self-relocation. I don't want to make everyone fall asleep. Basically, I just wanted to show one or two things. All those kind of addresses in JL are PC relative. So this, if you moved $underline start to a register, it will be a PC relative address, not an absolute address. How do I get an absolute address? You do a jump and link, put the destination R1 source. It's a PC relative jump, you get an absolute address at R1. So here's all I'm doing here. I'm saying, where am I? Okay. And if I'm at KT0, I'm done, right? I'm here. If I'm not at KT0, then I'm going to copy myself. That's what this is all about, to KT0. Then at the end, I'll jump. After I've copied myself to KT0, I'm still running at the wrong place. So I've got to get an absolute address in R1, subtract where I was from it, add the right KT0 to it, and do a jump there. And now I'm running at KT0 plus, this label. So this is a simple loop. It's really shitty, I will admit, really crappy RISC-V assembly code. Anybody with any expertise could do a better job than I've done, but it works, right? So, I don't care. I mean, this is the other nice thing about Plan 9. There's a huge amount of write once assembly code because there's so little of it and nobody cares once it works. That's one of the things I like. Now, final thing this is the board I'm going to do the demo on. JL creates broken ELF files, and the first thing I went to do is, I'll fix the ELF file JL wrote. Now I realized I don't want to do that because then I got to work with Grub, and I hate Grub, right? So I was part of the group that got rid of Grub all through Google, so I didn't want to go there again. So I thought I'll use kexec. So Linux kexec has a kernel option to build the kernel with the kexec option, and kexec means kernel exec system call. You say to the kernel, hey kernel, here's a kernel, replace yourself with this kernel, right? It's what we use I used to use at Google to do booting. Well, somebody got super clever because there's a thing called the purgatory, which is also built as part of the kernel. And the purgatory is a standalone piece of code that kexec in the kernel copies somewhere out of the way and then jumps to it. And then that thing moves the new kernel into place, and that thing moves to that, jumps to that, right? Somebody got clever with the ELF options, and the RISC-V kexec code, the building code, builds a purgatory that the kernel can't understand. So you went to use kexec on RISC-V, and it would say, sorry, I don't know what to do here. I can't process this. So that was a problem, but then I realized the kexec purgatory is pretty darn big in Linux and pretty darn complicated, and Plan 9 is pretty darn small and pretty darn simple. Could Plan 9 just be its own purgatory? And the answer was, yeah, I just run kexec, and I don't give it the purgatory. I give it the Plan 9 kernel, and it works great. So it was this unexpected thing that I didn't actually think it'd work, and it works fine. That's going to be the demo. And so I have a program for anyone who's doing this. I've got one other person who's reproduced all this at their place, both with hardware and the QEMU. But basically, you know, you open a file, you read that file into the payload. Here's the kexec, and basically, RISC-V kexec requires that you give it a flattened device tree, even though we're not using it at the moment. So there are two segments, and one of those segments is a flattened device tree, and the other segment is our kernel, and away we go. And notice, I ask it on the hardware to load the kernel there, right? And it'll do it or it won't. So here's the demo. I'm going to do it on the hardware. I've got this Mac, which is now my big battery to run the hardware. And currently that hardware is consuming 340 milliamps. And so what I'm going to do, I use my CPU in Go, which I've been using for almost 10 years. I use it for device under test at Google, right? And it's actually used at load bearing in Google in a number of products. So I'm going to use my CPU in Go. I'm going to run a Docker command on Linux. But the Docker command as its entry point will start my CPU. So the Docker container is on Linux, but all the programs are running on the Banana Pi 3 with CPU. And I'm just going to run kexec, and then it's all going to work, or it's not. We never know, right? So here I am on the command line, so I'm going to run this command called, it's just a script called k10 docker. And the trick of the script is oh, by the way, lib64 does or doesn't exist depending on what distro you're running, so that's what that mount failure is. But if I do like a pwd, right, I'm here, and I do an ls, that's what's on the Linux side, and my command is, right, and then I'm going to tell it to use, and all you people know Plan 9. You all know the beauty of this, right? I didn't have to copy anything anywhere, right? I'm using CPU. It's just that I'm using on a Linux host to another Linux host. And I'm going to have to there's the Banana Pi 3 console. And now we wait. You're going to see me, you're going to see a lot of this repeated crap. I'm reading an entropy register, which it turns out they didn't implement. So it's sitting here, you can see getting errors on bad CSR. And so now we're waiting for things to kind of spin up while it generates more entropy, and there's my RC prompt. And so now I can do stuff like PS. It always drops the first thing I type, and ls, and I've got stuff in bin. Right. I don't have LC, so you're not going to see LC, but it's Plan 9. I have no network. I have no USB. This was built with a /port, syssource9 port that Moody gave me, right? And that I had to hack up to get some stuff to work, okay? So let me quick reboot this. Well, no, I'm not going to bother. I recently built it with just using tip a tree 9 front syssource 9 port, and it hangs, right? So there's some kernel level page fault that I've messed up that I gotta figure out what's going on. The one nice thing about this though, the policy we're following with this port is it behaves identically in QEMU and the hardware, so that we have identical bugs in QEMU and hardware, and that's been immensely useful to kind of have the backstop of QEMU with the hardware. So that's where it is, and like I say, Richard Miller has said, I don't know about this zero-based kernel thing you're doing, and Jacob Moody said it, and Synapse said it, and you said it, and so nobody likes this idea except me, but you know, I've been doing RISC-V a long time, and working with machine mode. This is why I like the idea, because I like the idea of compatible pointers between the kernel and machine mode, because machine mode is really critical to the functioning of a RISC-V. I tried in vain years ago to get them to build processors without machine mode and failed, so as long as it's there, might as well use it. But the other thing that I think would be incredibly interesting if we could pull this off, if we could, when we boot, say, you know what, you're going to boot and stay in machine mode, and we're going to run the kernel in machine mode. And say, oh no, this time when you boot, you're not going to stay in machine mode. You're going to pop up to supervisor mode. The ability to compare those two things with literally the same binary, that would be something nobody can do. And we could really actually figure some things out about, you know, is there an advantage to doing it this way or not? Do we see a change because the kernel isn't polluting the TLB, for example, just as a simple one. So I actually do want to preserve that model. And the other thing I can do, if I do a zero-based kernel and I'm addressing the physical memory, I can actually determine at boot time, when I look how much memory I have, whether to use 3, 4, or 5 level page tables, because you can make that decision dynamically in RISC-V. It's just a couple high order bits in the root pointer and you're done. You say, okay, I only have enough memory to really need a 3 level page table, that's what I'm going to use. And that's just kind of a very powerful thing to have. That is it. So.
Yep. Thank you so much. As usual, people who have questions, please queue up here. If there are more questions, feel free to come closer already, so we don't have to wait too much.
And I'm here the next 2 days, so I'm happy to talk.
Yeah, great talk. Excuse me, I don't know how to word this, but with all the interesting things that come with a somewhat new architecture like RISC-V, and the inflexibility of Linux and more established kernels, do you see this as a opening for Plan 9 to maybe get more relevant, or
I think it certainly in a research sense, this would essentially give us a probe for implementations, right? So if we get to the point where we can say we'll boot in machine mode, then we'll boot it in kernel mode, and then we're going to run the same workload in each, and then we're going to look for a performance delta. Nobody can do that, as far as I know, right? And we had a long talk with Christopher Hellwig in the Linux core community and just said, what do you think? And his response was, just no. And he doesn't hang back. Yeah.
Hi. I was wondering what exactly made the Linux purgatory for RISC-V to break?
Oh, that's a really great question. So what happened was, and I wrote one of these too around 2000, right? Oh yeah, so the question is, why did the Linux purgatory break? So I got a paper in a 2004 cluster conference called Give Your Bootstrap the Boot, if you want to read about 5 different, oh, there's a thing there. Please. Oh, whoops. So it's a paper called Give Your Bootstrap the Boot, and it looks at 5 different examples of this. The kernel's going to boot the next kernel. And kexec by far, Eric Biederman wrote it, it was by far the most capable. So you could be in a 64-bit mode Linux kernel and boot a 16-bit mode kernel. So that is actually incredible for the x86. But what he had to do to make that work was make this really complicated and powerful purgatory. So my first purgatory when I wrote it was 8 lines of C. His purgatory, because he wanted printf and he had all this capability, is huge. And it needs to be relocated in the ELF sense. So there are symbols that need to be adjusted in his purgatory depending on where you copy it to in memory. So there are ELF relocation records in the purgatory. And at some point, somebody kind of got clever and said, we can add this really cool ELF relocation record and save time and strings. I didn't even remember what it was, right? But the problem was that purgatory ended up having a relocation record, I don't know what it means, of type 34. I don't remember what it means. You can look it up. And the kernel would look at this purgatory and say, I don't know what to do with this relocation record type. I give up. So I built a kernel with kexec. It built its purgatory. I set it up on this banana pie. I went to run it, right? I thought, what have I done wrong here? You know, it keeps doing this. What am I doing wrong? And then I went out and looked and thought, oh my God, they're building a purgatory with ELF relocation records in it that the RISC-V kexec code can't process, because the relocation code for every architecture in kexec is different. So would have worked on AMD, would have worked on ARM, would have worked on all kinds of things. It just didn't work on everything. Yeah.
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 Since we're talking about purgatory, I know the pleasures of having to fix it. Let's say there is an alignment issue in there, and it has its own trap handler, which doesn't actually handle traps, but it's just a hack. Anyway, so, but I do recall that it's also doing integrity checks, like X509 certificates, if I'm not mistaken.
Yeah.
So we're missing that kind of feature, but I was also wondering why it would actually be implemented in purgatory and not just as part of the kexec syscall. Like, why would it have to be running in purgatory?
The level of complexity of the purgatory, I don't know. I sometimes think things were done because someone thought it'd be cool if it could do it, but I'm not really sure. I just think it's, and by the way, if you get a look at the dev reboot in Plan 9, if you get a chance, look at the, Plan 9's had this as long as Linux has had it, but as usual, the Plan 9 code is just really beautifully compact. You say echo kernel name greater than dev reboot, boom, you're running a new Plan 9 kernel. So that's worth looking at.
This is a question for Richard, but he's not here. Can you summarize Richard's objections? Like, what is his, why does he not like it? What's it break?
I'd have to look at his email. I think he. Here's the problem. I think I know what his concern is. I think he's still thinking in terms of the kernel being able to address user mode. Okay, and if you kind of look at what I'm saying, I think, you know, he's a very smart guy, right? He knows that sooner or later this happens. And now we have a kernel of virtual that you know is different memory for this process virtual. So he's looked at this. He knows that this happens because he's always ahead of everybody, and he doesn't like it. But my counter argument is that the world is moving to this supervisor mode access protection, and sooner or later we're going to deal with this anyway. That's kind of my counter argument. So, but I think he doesn't like the fact that I'm coming up with this. Well, the other thing I said, would it be what I really wanted, by the way, I've looked at how much PC relative stuff JL does, and it's really good. It does a lot of PC relative, so you can load things anywhere. And I said, Richard, what would it take for me to be able to load this anywhere and run? And it can't quite do it. And the question, I think, is, do we ever want to be able to do that? Now, if you did do that, you've got, again, this big thing that all the Linux people say is important, is address space layout randomization. Do we care? Do we not care? I don't know. But it's possible if we were.
Is that just an issue of when the kernel wants to read stuff in user space, that it needs to walk the page table to find any users?
No. It
Maybe Brian can repeat the question.
So the question is this all an issue of the fact that the kernel has to walk a page table and it wants to read something in user space? No, I think Richard's just more not happy that this can happen, right? And I said, what do you think it would take to make it be able to run anywhere? And he said, you're going to have to tell me what we do about some of the code Jeff wrote that embeds a lot of absolute addresses in the image, right? And I said, well, I don't know what to do about that. So yeah, that's kind of where we're at.
So I'm wondering if I misunderstood something. I believe you said that the machine mode does not do virtual addressing.
Yeah.
Okay. So, and that you were putting the kernel at 4 gigabytes.
Yeah.
Okay. So If you're not doing virtual addressing, does that little device have more than 4 gigabytes? Or okay.
Yeah, the latest iteration of the $40 device is 16 gig. Machine mode can address the full range, but OpenSBI tends to hide out in the low range.
Okay, so the
That's
other
why I
thing
don't
is
trust
that
it.
I've seen a bunch of ARM devices, like
Yeah.
trying to remember. I think it was one of the NXP things where they
Yeah.
put the memory at a completely absurd location that is not 0.
Yeah.
Is that something you would have to start dealing with?
I don't know. What I'm seeing is there seems to be a convention around starting memory at 2 gig, and no matter how big it is. So I don't know. Yeah, it's a good question, and don't have an answer at all.
Yeah, so I just wanted to touch on kind of some of the thoughts about the VA space, because there's been some questions asked about it, and I feel like one of the big reasons is like we have pretty uniform VA layout across kernels right now. So like all programs will start at around the same base address, and that differs due to like actual alignment requirements on the system, and we lose that. And so I kind of wanted to talk about the point of the like TLB thrashing that you brought up. Like one of the problems, if you have different page tables and you have kernel and like user VA space, and they're not marked with maybe different ACIDs, or you can't mark kernel as with like a G-bit for global.
Yeah.
So like my understanding from seeing this and from some of the discussion we've had is that this may actually worsen TLB thrashing performance versus help it. So that's why I wanted to ask if you.
But are you
measured.
assuming no ASIDs, or
I guess I should ask. Are
yeah,
you utilizing?
ASIDs are a given.
Yeah. So
you
currently
have-
we do. Okay. So
Yeah.
if you kind of reach the limit, which I think is like 6 bits or something for ACID on, or is it less than that?
I think it's more on a RISC-V. I forget what it is, but yeah, you're right. I should look, but I think it's bigger than that. Yeah.
So yeah, that's one, I guess, advantage. When you don't have the separated like kernel and process address space, then you can also map all of the kernel pages with G-bit, so they're kind of like sticky in the TLB as global across all different.
You could do that. That one of the super annoying. Well, I don't know, not that annoying. I kind of wish they let you have a 512 gig PTE via leaf node, but they don't. So
yeah, it's just
you're
like
stuck
1
with
gigabyte
gigabyte leaf
exactly,
nodes.
Yeah.
But
Yeah.
oh
I
well.
guess, yeah, just to kind of like circle or like collect all the different points, I think there's definitely some advantages to be gained in the current structure that we have, where you have like sticky like global bit, and you have no trampoline page where you have like the kernel and user space mapped in the same. Like, I mean, the problem with Spectre and Meltdown on x86 was speculation across privilege boundaries. And I would be very, very curious if there's an actual SoC that we would want to run Plan 9 on that actually speculates across privilege boundaries. And if anyone knows of
wish
one,
I
I'd
knew.
be curious. Yeah.
Yeah.
Like, that's the point being, like, I'm not sure if that's even really a concern that we care about on the system of like having to deal with those Meltdown Spectre points. But
I mean, that's a really good point. And the only thing I know is I'm starting to feel like RISC-V is like a road with giant potholes, right? And every new standard is another one of the potholes. And so I'm past the point of assuming anything is safe. But yeah, I mean, that's a really good point you're making, though. Yeah.
major frustration of like having extensions and just having to like really
I know.
like I can't even have a standardized interrupt controller. I got to check, do I access it through CSRs or MMIO? Like it's
I think where I want to go with this, by the way, is I want to assume MSIX, because their first
thank you, by the way.
the first set of interrupt controllers were pretty ridiculous, right? So my plan is to assume MSIX and leave it at that. So
Putting my hat on here as RISC-V ambassador. There are things that are actually being standardized over time in terms of, for example, we got the profiles now, which are meant to be collections of standardized parts, including interrupts and stuff. But yeah, there is always still going to be work toward more being standardized in that regard. But yeah, let's say how interrupts were handled up until now were like a bit of explorative, and now it's being standardized over time more and more.
yeah, the other comment about by the way, when this is running Linux, it was 0.35 amps, and now it's 0.76. So power management in Plan 9 is a ripe area for exploration. Let's put it that way. But what was the other thing? Oh, yeah, no. So the thing that impressed me about 9K dealt with a lot of wacko parts, like the polar fire, all these weirdo parts, right, that didn't follow any particular standard. This board is a Banana Pi F3. It says we're RVA23. I'm actually running vector workloads on this for some academics who want to get numbers out of it, and the standards of the RVA23 basically implements quite well. So I do feel like that it's sort of like the Big Bang, you know. So we're like maybe in the slightly more stable part of the creation of the universe, but it's getting a little better, as Daniel pointed out. So.
You're looking forward to also being able to use the hypervisor mode at some point?
Oh,
then you could span your operating system across all 4 modes.
So that was like the other part of the paper that I didn't have time to write. So the first thing is there is no hypervisor mode, right? They have this beautiful design, which is worth reading because it's literally like 10 pages in the privilege manual. Here's how we're going to do virtualization, and it works great. And if you're used to an x86 VMX mode and look at how RISC-V works, you're going to wonder where all the complexity went, because it's really good. So I really like it. However, I don't intend to use it because it has another capability. For anyone here who knows what logical partitions are, which is what IBM Power does, where you basically are able to say, I'm going to take this range of memory and I'm going to put you in there and you're going to live in that range of memory and like it, and you're not going to get out. Okay? And the RISC-V architecture has the ability to implement logical partitioning, and that's one of the things that I want to have Plan 9 do. And why is that? Because virtualization comes with always a 10% hit on performance, but when you use logical partitioning, it doesn't, because you're walled off in terms of what you can do in memory, but otherwise you have the raw hardware. So I'm much more interested in, it's called LPAR for short, that it's IBM's claim to fame on the power systems for like 30 years now, and it's a really wonderful way to do multi-tenant. So that's what I'm going to be looking at. But if anybody wanted to look at getting virtualization working on the RISC-V, it'd be a great project, and you would find it far easier than like the VMX on x86. It's just way cleaner. In fact, they had a hypervisor mode in RISC-V, and this is another thing about being a clean sheet. They got rid of it. You can actually find the wording in the document. I have a talk somewhere here about that. Literally the wording in the document says, yeah, we're not going to use hypervisor mode. We reserve that mode for use at some other time, but that's not required for our virtualization. So it's that part is just really worth understanding, that part of the standard.
Yeah, for those who are not following along all the time, so the hypervisor mode has been reintroduced.
Oh no, it has?
It has. There is processors now available with that mode
in
hardware.
With virtualization or with hypervisor mode?
With hypervisor mode in hardware.
Oh my God. Okay. Well, the standard says they're not using it. Okay.
If I'm not mistaken, it's even part of the RVA23 profile. Or profiles, because it's not just one. Oh, I don't have that talk here. Darn it. Huh? What's this?
Can we, actually, I'll just ask.
Yeah.
Can we pretend that, Can we pretend that the hypervisor mode doesn't exist and still use what you were talking about?
Yeah, we can. And the other thing, Richard Miller pointed this out. Somebody said, "What are you going to do about vectors?" And he said, essentially, we're not, right? And I don't know if that's really the way we want to go long term, but that's the current take. There are certain features we just don't use. So anyway.
All right, looks like that's it. So thank you very much.